方老师，您这边部署10个数之后就可以开始主持了。
多长时间以后啊？
10秒钟，您默数十个数。
好。Okay, good evening and good morning, everyone. Welcome to today's webinar. My name is Fang Fang. I'm VP Events for Alberta AI Association. So today I'm going to hosting the webinar given by today's speaker, Dr. Alvin Sun. Once again, for those of audience who regularly attend our event, you already know this event is held monthly, aiming to sharing the research achievements and advances of AI technology contributed by the speakers and their work. And this event is co-organized by CNKI, China, and Alberta AI. Now, please let me introduce today's speaker, Dr. Alvin Sun. Dr. Sun is the co-founder of Matrix Labs Incorporation and the tech lead of the remote sensing research team at Multimedia Research Center of the University of Alberta. His master's research focused on hand motion analysis and HCI systems. He interned at TCL Research America in San Jose and was granted 4 United States patents in the areas of computer vision, human body recognition, and face verification. His PhD study focuses on using deep learning and signal processing techniques to accelerate satellite signal processing pipeline for a wide area monitoring from aerospace. He's now in charge of the R&D department at Matrix Labs Incorporation, a Vancouver-based Web3 firm. At the University of Alberta, he supervised the multimedia master program project focusing on blockchain and the digital world. So today, Alvin will give a talk about radar signal decomposition and quality assessment for wide area monitoring. The lecture will take usually 1 hour, first about 40 or 45 minutes speech, and then question and answering section. You can ask the questions under discussion section either during the presentation or after, and Dr. Sun will answer them after the speech. So let's welcome Dr. Alvin Sun to give his presentation. Very pleased to invite him coming today. So Alvin, so go ahead, please.
Okay, thanks, Dr. Fang, for your introduction. And also appreciate everyone who attends this webinar. And so before that, I just wanted to double check the screen I'm sharing is the correct one, right? It's just have the slides. I just want to make sure that.
That's good.
Okay, cool. Okay, I think we can start. And first, really appreciate Alberta AI's invite to let me have the opportunity to present my PhD studies here. And because of the time constraints, so it has to be a high-level walkthrough of what I have been doing and the outcomes of my PhD studies. My thesis is titled as the radar signal decomposition and quality assessment for wide area monitoring. And today's presentation is organized as here. I will begin by providing a brief overview of the INSA and give the problem definition, followed by the scope and objectives, as well as the overview of the thesis and the contributions. And lastly, I will give the conclusion and the potential future works. So let's start with the background of the INSA. It is a specific radar modality I was working on. And before I get into INSA, I would like to explain what SAR is. The SAR, synthetic aperture radar, is a microwave imaging technology. The SAR antenna emits microwaves from the aerospace and captures reflected backscatters from the Earth. The recorded digital SAR image is actually a 2D image, and each pixel corresponds to a small area on the Earth and provides a complex number containing amplitude and phase information. The SAR image is also known as the single look complex SLC image due to its data format. And the amplitude value of each SAR image depends more on the ruggedness of the object on the terrain, while the phase mainly describes the delay between the transmission and the reception. But however, due to the signal's periodic nature, travel distance that differ by an integer multiplier of the wavelengths introduce exactly the same phase changes. So that results in the phase value is wrapped by 2 pi. And in practical, due to the huge ratio between the resolution cell dimension and the wavelengths, the phase change passing from one pixel to another one looks random and is of course useless. So that is the main reason in the early literature, only amplitude components is used in SAR applications. But later, the interferometric technology is introduced to SAR, which is known as the InSAR. So it can be used to detect and measure ground displacement over time by comparing multiple SAR image pairs. And in an InSAR image, each pixel represents the difference in phase between 2 SAR images. So this difference in the wavelengths encodes contaminated signals, including the displacements. And that makes InSAR has emerged in recent decades as a promising technology for monitoring and describing the Earth. So next, I will state the problem definition of what challenges I was facing and objectives we are targeting. As I have mentioned, the problem is the phase value in the InSAR image or the interferogram is the phase difference between 2 SLCs captured at 2 different dates. So it encodes not just surface displacement between the 2 dates, and the InSAR observed phase mainly includes different phase contributions affected by different elements. So it includes the ground movement, as well as the topographic contribution, atmospheric distortion, and the satellite position, as well as the noise. And furthermore, the observed phase is wrapped by 2 pi, which makes the whole problem becomes really challenging. So overall, a typical InSAR processing pipeline, we start with the microwave echoes, which can be used to generate the SAR SLC image, and a pair of the SAR image generates the interferogram. And in a typical processing pipeline, we first want to remove the phase noise components to get the field rate phase and do a quality assessment to indicate each pixel location's signal quality. And because this indication is crucial for our subsequent analysis. And next, we can use the satellite orbit data to get rid of the phase contribution from the Earth's ellipsoidal surface. And at the same time, use an external digital elevation model to remove the topographic contribution. But however, the external DM is infrequently updated. So there will be significant residuals after applying the external DM. And thus, it usually transfers the total phase component to the DM error or height error phase components. So after that, studies are working on extraction and separation of 3 left signals that are hardly pre-removed by external data. And typically, the final signals of interest are hard error and deformation, because hard error is the DM residuals that can be used to refine the external DM to get more precise description of the Earth's topography, and the deformation is obviously a good indication on the ground displacement. And then I will quickly go through the thesis scopes and objectives. So my thesis title, Radar Signal Decomposition, refers to extract and separate the signals of interest from the composite one. And the quality assessment refers to 2 main tasks: estimate the quality of the observed signal, and the second one is to evaluate the quality of each processing module's output. And wide area monitoring means our typical study input with the full resolution has the size of around 600 million pixels. So this means that all of our proposed algorithms must be robust, automatable, and time efficient in order to meet the requirements of the wide area monitoring scenario. And in summary, my studies on the described research problem can be classified as the following levels. First, I want to remove the noise term first and estimate the coherence, which is the pixel level quality for each pixel in the input. And next, I propose to separate deformation and DM height error signals. And the last is I also propose the inside data simulator to have a controlled environment to do the validation. So let's start with the removal of the noise component. And I first demonstrate using a deep learning framework to remove the addictive Gaussian noise from the natural images. And the research gap in 2017, when I just started my PhD, it shows that the convolutional neural network almost dominate this research field. But however, when the noise signal level is high, such end-to-end CNN model can remove the noise well, but may lead an overfiltering. So that hard to recover the fine structures. And we realized that it may be because the information is actually lost due to a high level of corruption. And to this end, we introduced a high-level dual-stage restoration framework. We first adopt a residual learning to do a preliminary noise removal. Next, a full image reconstruction denoiser is applied for recovering the fine details. And in order to recover the potential lost information, we apply a generative framework. And adversarial training is used to perform as a clean image prior regularizer to guide the both denoisers output the filtered images towards to the clean image distribution. And we got better results than state-of-the-art methods at that time. And the model can preserve sharp edges and fine structure details better than other end-to-end models. And our key findings are the residual learning is very effective for removing the addictive noise. And CNN works well for such end-to-end setup as a good function mapping learner when we give it proper training samples. And based on these findings, we decided to adopt a deep neural network for our INSA study. And here our input is a simple noisy infogram, and our output are filtered infogram and a corresponding coherence map. And in addition, we need a non-stack based method which only require a single infogram with rapid phase. And the research gap in 2017, when we first started to work on this topic, the filtering and coherence estimation are usually sequentially applied, and filtering usually relies on the coherence estimation. And another unresolved trade-off is that the stack-based method requires more inputs, but gives the better results than the non-stack-based method. But it usually requires more than 100 interfograms, since it may not satisfy for all real scenarios if we just started to monitor a new area without the historical data. And then we proposed the deep INSA, so which is an early bird using the deep learning based model for solving this problem. The model is designed to do the filtering and coherence estimation in a single pass, and it outperforms all other non-stack based methods, as well as achieve on par and even better results than the state-of-the-art stack-based methods. And to quantitatively assess the proposed method, we design an INSA simulator which can generate motions and noise patterns randomly. We also adopt a teacher-student training strategy, which allows the deep INSA to work on real-world data. It augments, automates, and accelerates existing undifferentiable teacher methods using a differentiable deep neural network. And here are selected sample simulation data generated using different distortion configuration. And deep INSA is the most matched to the ground truth. And the quantitative evaluation shows that the deep INSA outperforms other approaches significantly on both phase filtering and coherence estimation. And we also conduct the real-world experiments. And well, the qualitative results shows that the deep INSA maintains a good balance between the noise removal and structure prevention. And regarding to the coherence estimation, the proposed deep INSA consistently gives better contrast and less bias in the low coherent area. And overall, the deep INSA is actually designed under the supervised manner. And to provide the target output for training the model, we used a stack-based algorithm as the teacher. And this is a very successful attempt, as the deep INSA's commercial version has been deployed in industry as the standard module in the processing pipeline of the company that processes PB level reader data every year. But however, due to the supervised setup, it does have a certain inherent restrictions. It requires good reference data for training, which is usually impractical for the small companies and research entities. such as the teacher method we used that requires a GPU farm to run, and real-world data is costly to acquire, store, and pre-process. So to this end, we start to look into some self-supervised approach. So it is not a new topic in the natural image research field. And there were already some well-known works, such as the noise-to-noise, which learns to restore images by examining the corrupted instance. But however, it requires at least 2 pairs of the noise images with the same latent clean version and the same noise condition, which is not possible for the SAR and INSA scenario. Later, the noise-to-void was invented, but it recovers the center pixel information by using the surrounding pixel information and introduces the concept of the blind spot network. But however, it is known with the limitation that the center pixel is masked and leads at inefficient training. And the model also tends to ignore the target location information during both training and inference stages. And my colleagues' work, Jan Insa, adopts the noise-to-void concept and plug the mixture density network as the output layer to predict each pixel location's distribution rather than the value. And then the mean of the estimated distribution is used as the filtered signal, and the standard deviation is used to derive the coherence, because that describes the uncertainty of the current pixel value depends on the surrounding pixel value. So this is a good proof of concept work, but with the same limitation as noise-to-void for filtering, and the coherence is derived with the handcrafted function that is not mathematically bounded between 0 and 1 with low contrast and resolution. But following this direction, I proposed the SRD INSA. So to boost the training efficiency, I first introduced the random masking. So rather than training on the center masked image patch, the random masking allows more flexible backbone model selection, and any image-to-image network can be used to learn to recover the randomly selected pixels in an image using the rest pixel during the training. And second, based on the past research, I force the model to learn the residual information, but not the residual value as in a DNCN. It is the residual distribution by integrating the mixture density network as in GenInsa. The model outputs the residual distribution during the inference, which requires the model to not ignore the masked pixel values throughout both training and inference, so which can be subtracted from the observed signal to yield the latent signal distribution. And in this case, we also use the mean of the distribution as our filtered signal. But finally, because we already have the latent signal distribution, we can use Monte Carlo sampling to simulate the capturing process for the same location multiple times with exactly same condition. And next, just use the definition of the coherence to directly compute the approximated coherence on the sample stack for each location. And the qualitative results on simulation data shows the SRD INSA is the most matched to the ground truth and have better performance than GenINSA. And improvement on coherence simulation is also significant. And the quantitative evaluation also confirms the results. The qualitative results on real-world data matches the findings in simulation experiments. And overall, the deep INSA is the first study in the INSA domain to use the neural network to mimic a complex algorithm plus the human operator behavior. And I also collaborated on the GenINSA to create a self-supervised training for filtering and coherence estimation. And finally, I proposed the SRD INSA to address the GenINSA's constraints and to make it deployment suitable. And next, I'm going to present the processing step of extracting the signal of interest. And after removing the noise, and we are now focusing on how to separate deformation and high-level phase components. So basically, if apply any linear motion rate model for each location and interphotogram K in time series, there is a well-defined equation regarding to the motion rate and high level respected to radar signal spatial and temporal baseline parameters that can be treated as a constant for a given stack. So thus, we can convert the signal separation task into a 2-variable optimization problem for each pixel location. And we have 2 parameters, which is linear motion rate and the height arrow. And we're trying to minimize a given objective function. And a typical objective function is the temporal phase residual coherence. So that is the temporal coherence index for the phase differences between the reconstructed phase and the observed phase. So while the reconstructed phase is calculated using the estimated parameters with previous equation. And almost all existing works only do the temporal analysis on high coherent locations, which is also called the persistent scatters. And besides, some of them may require phase unwrapping first to have to solve the unwrapping problem simultaneously. It makes the whole process very complicated because phase unwrapping is a very time-consuming and challenging task. And other than that, algorithms that works on the rapid phase gives poor estimates for fast-moving areas and prone to local optima. So how challenging this optimization problem is can be easily visualized by inspecting the loss landscapes. So there were 2 loss landscapes with synthetic ground truth motion rates and height arrow with real-world baseline parameters. So it can be seen that because of the phase wrapping, different baseline parameters cause a very different target function actually. And they are non-convex, ruggedness, and have many local optimas. And in fact, a simple grid search is often employed in industrial processing pipeline. A typical grid search was used by our industry partner with around more than 20,000 sampling in total for each PS location. So with a restricted precision bottleneck due to the sampling step size. But however, by observing the loss landscapes at different sampling scale, we realized that the global optima can be relatively roughly located with the less dense grid sampling. And based on that finding, we plan to first follow the literature to do the temporal analysis, and we proposed to use the derivative-free stochastic optimization to search the results in the solution space. And I propose a 2-level stochastic searching. So at the first level, a coarse iterative grid search is used to locate a set of candidate solutions that may near to the global optima. And then the fine local searching algorithm is used to find the local solution starting from each candidate solution, and then choose the best one as the final results. And both quantitative and qualitative experiments demonstrate the proposed methods results on both simulation and real-world benchmark datasets. And the model should match the results comparing to the least square feet on unwrapped intervalgrams by optimizing on wrapped ones. And the IGSMAES achieved the satisfactory results by balancing the exploration and exploitation in 2 stages. But however, our industry partner has a business requirements that a dense estimation is required. And they also want to explore if the atmospheric removal procedure can be avoided because it is a time-consuming and error-prone phase. So here, our recent the study, my last work of my PhD is the Canva ArcFit, which is the spatial temporal optimization framework for ground deformation and DM error optimization. So in this study, to address the constraints of the temporal only analysis, I introduced the Canva ArcFit. So it is a 3-dimensional convolutional optimization technique involving the use of the stack of the 2D intervalgram rather than the persistent scatter points. So it estimates the height arrow and motion rate at per pixel level of the wrapped intervalgram. It can be run early in the processing chain before removing the atmosphere as well. And the algorithm is based on the same phase model as previously one. And here the common approximation for the spatial coherence of the complex image, whose phase signal is the summation of the multiple signals can be read as follows, for instance. And due to the spatial smoothness of the atmosphere, its coherence in small area can be treated as 1. And if we subtract the estimated phase from the observed phase, the spatial coherence of the phase residues increase as the model of the signals get close to the correct value. And additionally, the same approach works for the temporal coherence. So to demodule the atmosphere, we need work with the double phase difference, and also known as the arc residues. A pair of neighborhood pixel and can be used to produce the arc in the same way that the phase residues are. And then the observed arc temporal coherence can be formulated like this. Here, the similar concept at the atmosphere will lead its components to be canceled. And we then have the similar equation for the model arcs. And if we subtract the model arc from the observed one, the arc residue temporal coherence increase as the model of the signals get closer to the correct value. And based on that algorithm, we define our optimization problem with two objective functions for maximizing the spatial and temporal coherence for each location. And we developed the two specific convolutional kernels for doing the optimization on GPU. One is specifically for calculating the spatial coherence. And based on that algorithm, and which is simply for calculating the main value of each window. And the second one is the random arc kernel, and its center pixel is fixed to 1, and randomly picked a neighborhood pixel as -1 for effectively produce the phase difference. And after that, a simple bottleneck kernel is used to calculate the arc residue and the arc coherence. So both loss function and kernels can be easily customized in any like the current deep learning framework, and we use PyTorch to implement that. And we just adopt the add-on optimizer to do the optimization on GPU. And using only count and arc objectives, the model is still easy to settle in the local optimus in fast moving and rapidly changing locations, or shifting to other global optimas due to the phase jump. And it can be easily observed in the simulation examples as shown in the bottom area, highlighted by the red rectangles. And to this end, we proposed two regularization terms for solving this issue. The first one is the total variation. So it smooths the estimated signals and helps make the loss function more convex, and make it easier to locate the solution when it is a bit far away. And apart from that, both types of signals are also penalized by L1 norm regularization, and this term is primarily used to avoid the global phase shift. But however, how to determine the strengths of those regularization terms are essential. Too high leaves a biased estimate, while too low results in less advantages. So we were motivated by the focal loss, and instead of proposed this formula to change the weight factor for each regularization term adaptively at each pixel location based on its objective value, which is the coherence in each step. And simultaneously, I still have a global polynomial decay to regulate the factor globally during the optimization process. And so our final algorithm and objective function is here. So it can be seen that the local adaptive already gives a satisfied result without any like the stuck at the local optima, but just a little bit global phase shift. So after applying the local and the global regularizations, it gives the best results comparing to the ground truth. And we further simulate more signal pairs with varying degrees of spatial complexity as the benchmark dataset, and tested on all possible configurations and combination of each proposed modules. And quantitative experiments shows the adaptive regularization provides the significant advantages, and the qualitative evaluation confirms that our final model demonstrates the best estimation from almost all the cases. And we also discovered that the arc loss provides a more precise coherence indication and prevent the ring artifacts in the final estimates. And experiments in the real world indicates that the model generates consistent estimates on stacks of with and without atmosphere signals. So this demonstrates the ability to eliminate the signals to estimate the signals without the need of the atmosphere removal process. And we also tested out the cases where both atmosphere and noise signals are there. And results are also consistent and satisfying because we have regularization terms, which is the locally adaptive. So the noise signals do not impact the places which has a lot of noise. And here is the GPU memory and time cost for 4,000 iterations on a 400 times 400 times 135 input stack. And arc loss introduced significant time cost we can investigate and the significant GPU usage. And because, as I mentioned, we always care about the wide area monitoring. So in real-world processing pipeline, a full image is actually divided into the overlapped stripe and sent to GPU farm to do the processing and gather all the outputs together and merge them to the final output. So to that end, in order to avoid as many as I/O process as possible, we further process a mini batch optimization to let a single GPU can be used to optimize larger spatial size stripe. And with less time and GPU memory, one can achieve similar or better results than the complete stack optimization. And this is treated as a huge benefit from the operationalization point of view. And so for this part, the contribution is we propose the RGS-CMES to work on the rapid phase directly using a two-stage searching-based optimization. And later we proposed the Convo ArcFit for doing the spatial temporal analysis. And this is the first algorithm to do the best of knowledge for dense signal estimation. And I'm currently leading the team to keep improving it by adding more features. And in fact, that the base version of this one has already been validated and commercialized. It is now served as the standard processing module by our industrial partner in Vancouver. And the last section is the INSA simulator. So besides all previous processing, there is a remaining challenge is how to precisely validate and eventually optimize the developer algorithms with no ground truth data. So in this work, to quantitatively assess the proposed methods, we design an INSA simulator, which can generate synthetic signals randomly. So most existing INSA research studies use even non-INSA tester cases in early works, or a couple of synthetic interferometric phases with the simple geometric shape ranges. But however, there is a lack of the large-scale benchmark dataset to do the quantitative evaluation, especially for deep learning-based methods, which are the data-driven techniques that require large-scale dataset for both training and validation. And in my study, we first proposed a 2D stochastic INSA simulator, which is able to randomly generate the synthetic noise field intervals and also highly configurable distortion levels and their combinations. So it has been used for our filtering and covariance estimation studies. And we further extended to a 3D version by generating the synthetic motion rate and high-level signals in time series. That is used for our parameter fitting studies. And lastly, we are also pursuing right now is to build a generative model to simulate the signals by learning the real-world signal distribution. So I initialized this study, and now one of my colleagues are working on it. So our latest results are amazing, and even experts cannot tell whether the signal is real or synthetic. And in conclusion part, I will give a summary of my contribution during my PhD study. So it includes some side works that is not listed in my thesis, but also benefit for the whole INSA community. So go back to our processing pipeline, start with the microwave radar echoes. The first side work, I used the CUDA to rewrite the company's in-house algorithm to boost the processing speed by around 60% when convert raw radar data into the SAR SLC image. And next, once we have our interprograms, I proposed the AEDNet, meaning for proof of concept, and the deep insights commercial version has been deployed more than 2 years in industry. And I also co-worked the Gen INSA and proposed the SRD INSA with deployment ready results. And for signal separation, we have temporal-based IGS-CMAES as the proof of concept, as well as the first spatial and temporal algorithm for dense signal estimation. The initial version has already been deployed in real-world processing product. And I have my INSA simulator with both 2D and 3D version that are already used by not just our research team, but also cited by many other research groups over the world. And I also work on designing and developing an AutoX deep learning framework in order to create a standard training and inference pipeline for all of our proposed algorithms to make them compatible with the farm-based operationalization architecture in the company in 3VG, which is located in Vancouver. And now here is the snapshot of my main contributions. So for future direction, from the filtering and covariance estimation, the SRD INSA now only consider the phase information and can potentially utilize the amplitude information as well. It is also now waiting for the operationalization assessing from the company side. And next is the combo arc-fit can further investigate the optimization on nonlinear motions. And on the other hand is because it is now a purely optimization-based model, which has to do the online optimization. So they are made possible to consider a hybrid optimization that uses a learning-based model to give a rough estimation, and then use the combo arc-fit to perform a quick fine-tuning on it to see whether we can reduce the number of, we can reduce the runtime. And lastly, as I previously said, the GAN INSA is currently being explored by my colleague, and we are working on to improve the signal resolution. And on the other hand, there is a side benefit because once we form adversarial training for simulating the real world signal, we actually train a discriminator as which can be treated as the real world signal prior knowledge that can be used for other studies. For example, our parameter fitting, like the task, because when we do the online optimization, the trained discriminator is actually a differentiable model that can give the derivatives feedbacks or the gradients feedbacks to the motion rate and the height error estimates to see how well it close to the real world signal. And we actually treat it as one type of direction for as a side benefits from our simulator study. And that's all. So I know like I left my emails here. So if you have any questions, you can either ask here or send me email, and then feel free to have any kind of discussion or any potential collaboration in the future. Thanks.
Okay, yeah, thanks, Alvin. Wow, that's too much research work during your thesis, and it is impressive. You get quite a lot contributions to the research community, and I'm glad that your approach is somehow commercialized, right? That's yeah, that's really a practical contributions. So because my research is not focused on such a specific research area, so I don't have so many questions regarding your research approaches or methodologies. So let's see if the audience have some questions regarding your research area, for example, like pipeline infrastructure, or gas mining. If you have any questions, welcome to ask. For myself, I do have only one question that you mentioned that deep inside, there is a limitation for the small companies or research entities, right? So could you explain why that's limit to a small company?
Yeah. Okay. Yeah. No problem. So in fact, that as I mentioned, like when we first started this problem, we actually get the requirements from the company. The company has their in-house algorithm, which is the traditional algorithm that is doing the very expensive optimization and online searching that requires 100 like the images. I mean, you can just treat it as the video frame, but I mean the different data modality, but you can just treat it as the video frame, like the 100 frames, and they need to run a very complicated algorithm on a GPU farm that more than 100 GPUs to process the whole stack and get the output. And once we get their requirements, we want to accelerate this process and to see whether the neural network, deep learning, machine learning can help. And because we already do some proof of concept on natural image, restoration studies, we started to look into how to migrate that into the INSA data modality. There were some the pre-processing steps that has to be done to make this kind of data modality suitable for the learning-based algorithm. But because of this is a supervised the setup, which means you have to give the ground truth, which is the label. And the good thing for us is the company has a tons of historical processed data, which is they have already tried their best to get the best outputs for the input. So you can just treat it as the ImageNet is the human has already tried their best to label, to classify the image class. And here similar things. And the company has already tried their best, try all their computational resources and human expertise resources to get the best results they have. And we just use that results and try to use we use the deep learning just as a good, as I mentioned, it's a good function mapping learner to map the input to the output. But the output is generated with the conventional algorithm that requires 100 image. But when we train a model, we actually set it up as a non-stack based algorithm. It's just the input is just a one image frame. And after the experiments, we find that the results is actually achieve on par results or even better on some areas comparing to its teacher method. But the reason why I said it has a limited benefits to the small company, because as a small company, if they don't have such resources, they cannot get the reference data. And the company we collaborate, I don't think they will open source the training data they have. And also for the small research entities, they also cannot get this kind of good reference data for real world data. So, but that is actually the reason why later we move to the unsupervised the manner. This is not just for the companies, also for the whole the INSA community, for both small companies and the research entities. The Gen INSA as well as the SRD INSA, you don't need any the reference data. You just give it the noise data, and they will try to remove the noise just based on the noise observation, and still non-stack based model. And I mean, from the performance the point of view, it cannot beat the one with the supervised training once we give it the really good ground truth or the reference data. But this one already gives the satisfied results, because even the company, they have a certain requirements once they study on a new a new site that is totally from the sites they studied before. For example, they want to study the mountain area, but all their previous historical data are the urban area or the mining sites, because we all know that the deep learning, especially for the supervised training, is a data-driven task. If your training data is quite different with your testing data, your model doesn't work. But once we have the unsupervised, like the model for the GenInsa and SRDInsa, you can work on like without any training data, even do the online optimization.
Okay. Got it. Yeah, because of still the data issue. Yeah, most of AI technologies, they do need a lot of referenced data, labeled data, so that they get a more intelligent model and more precise results. And but fortunately, there are unsupervised technology or reinforcement learning technologies that always we would like to develop those technologies to dealing with the less data or lack of data or bad, not that satisfied data to to develop the approaches dealing with that.
Yeah, exactly.
Okay, I think can you Dr. Sun, can you show your email address again? If there are audience, they have specific questions, they can contact you by email, or you can contact Alberta AI or CNKI in China. We can transfer the questions to with Dr. Sun. So you are welcome to exchange your idea in research. Hopefully we can, moving forward with any research contribute to AI field. So if there are not more questions coming, I think we can conclude today's webinar. Still, Dr. Sun's presentation today will be recording and will be published YouTube channel of Alberta AI, as well as the CNKI, in posters. You can still watch later for the recording video to learn and to get some ideas from that. Okay, so let's conclude today's webinar. Thank you everyone to attending today's presentation. Thank you very much, Dr. Sun, to give your thesis research work.
Thanks for the invite.
Okay. Yeah, you are very welcomed. And let's see next time, next month's webinars. Okay, so good night and good morning or have a good day, everyone. Let's see next time. Thank you. Thank you for attending. Bye bye. 已经结束直播了吧？
结束了，黄老师。那个您刚才那个啥，我同事他们在呢，他就会切了，就会把那个信号切掉。
OK， 那我们的 YouTube 还在直播呢。
这个是不是得应老师呢？您稍等啊，我看我能关吗？这个。